I believe so, but that'd be the first thing I'll mention when we start. Okay, I think I'll go and get started. I see handful of folks are joining online, so welcome to you all online. Maybe you can just let me know if you're hearing me okay. But let's open up in prayer and we'll get started. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course, Lord. I pray that the material will be clear. Pray that it's going to be helpful for them as they're getting working through their programs here at APU in computer science, computer information systems, or engineering. Also, Lord, I pray that you would be guiding their time here in terms of their spiritual formation as they get a chance to get a better sense of the story, the narrative in Scripture, and how to be deriving theological principles that we can apply to our day-to-day life and give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're continuing to make some good progress here in going through a lot of interesting, at times technical information. And so we went through the introduction that gave us a nice overview of what computer architecture is about. And then with this computer system, we have gotten a variety of chapters getting into memory. And so the different ways how it's used, the locality, if it's local or not. We got a chance to be talking about cache and how it actually improves performance. We then got a chance to be talking about internal memory and external memory. Internal memory is you can think of like your RAM, but there's other places internal memory shows up in the CPU in terms of registers. And then external memory, where we got a chance to be thinking about hard drives. I showed you example of one that I have, an HDD. Then we got a chance to be talking about input and output. And today we're going to be talking about operating system support. And so what I'm going to do is I'm going to give a little bit of an more introduction through the part of the lecture notes called the greatest hits, and I'll just be hitting these things up to chapter 9 to give you a reminder of things that we've covered. We have the von Neumann architecture, which consists of the CPU, memory, and the I/O. And Stalling, he has this fourth category, the system bus of how it all connects together. Inside the CPU, we have some characteristics that are like what we see in the general computer architecture, where for memory, it has registers. It has this computing environment, which they call the arithmetic logic unit. We're going to get into that in more detail. And then there's also the control, the I/O. Maybe you could put that in that kind of a sense. And then we can go even deeper, getting into the hardware and the implementation, but that's beyond what I want to be focusing on. I've been trying to give you a chance to be looking at some bits of hardware as we go. And so this is one of the illustrations that's in the textbook. And so it actually plugs into a motherboard specialized more for the server environment, where you can have these CPUs are hooked into that, and it's actually can be in a sense operated as its own computer because it has all of these kind of peripherals. You could hook up a monitor and stuff like that. We talked about how over time, what has changed, what is the trends. And so we're getting to a point where we can't make things go faster. The power per square inch is getting higher, would actually start to cause things to melt. And so now what we've started to do is increase the number of core. And so that's one of the ways that we're now starting to work on getting performance to increase. So once again, we see a little bit more detailed view of a von Neumann architecture and the fourth element that Stalling likes to talk about. And we get into the innards. Here we see an illustration of the execution unit or arithmetic logic unit. We have mentioned registers and there's general purpose registers, and there's also ones for specific purposes like the program counter. We have that. We have the IO modules, your keyboard, your mouse, your monitor. Those are all IO that needs to be managed. And then we have memory, and it's showing the distinction between what we have for instructions versus data. They have a slightly different performance. And I have a graphic that'll show that in a minute. We're going to be getting into parallel architectures and the basic instruction cycle, but this is a very fundamental level. Is the fetch execute is what we do over and over again. We have this pyramid for the memory, where the fastest type of memory that you're going to have is going to be in your CPU, and so those are the registers. We then have cache, and we have multiple layers of cache, and I'll have a chart that will show that, but it's still not quite as fast, doesn't need to be as higher performing as the registers. Then we get into the main memory. We talked about different technologies that are used. And so these are just some of the acronyms that we see there. We saw that for the solid state memory, flash memory, and this is, you most likely have this now in your computer, an SSD. So that's the state of the art in terms of having your larger type of memory that you would be using for your storage, your computer programs and stuff like that. A little bit more legacy is the HDD, having a magnetic disk with platters that you record the information. And finally, the slowest thing that you would have is the magnetic tape. This shows a graphic of there's a bell-shaped kind of relationship, but still in general, the mean is different between what you see for instructions and versus the data. The data is a little bit, has a wider variance, and so it's not as predictable as what you would be getting, like going from 1, 2, 3, 4 sequentially in an instruction set. You would have loops, and so there would be some variability and things like that start to take place. So there's a couple different ways we can access specific bits of information sequentially. That's largely what we would see for if we have instructions, direct access. And so here there's read and write mechanisms. We can go in and out to specific parts of memory. You could have random access, and so you don't necessarily know what's going to happen. How much memory am I going to need in the next 5 minutes? And so there's multiple things that are taking place to help you figure out where to stick what where. And then there's associative. And so one bit of memory can refer to another bit of memory. Or you can be thinking about, if you're going to have cache, well, what do you pull out of the main memory because to go faster? And so that's one of the topics that can start to come out for that. We talked about cache, and so initially there wasn't any, and then with design architectures and research and testing, they found that did actually improve performance. So you can have a faster cache and slower main memory, and the overall performance actually improves. And it was then found that you could have multiple layers of cache. And so we then got into the specifics of how would you go about setting that up, how big, what would be the rules that you would have for each of these? What do you refresh, and what have you? So there's various ways that is set up. So here is a typical cache organization. So we could do one of two things. You can connect directly to the processor. And so what happens is it either catches it because it's in the cache, and so it's going to report back, or if it doesn't, then it needs to go to the system bus, go out to memory, retrieve that information, and then have the data go back to the processor. So you either have a faster loop going here, or you have to do this longer loop of retrieving that, and you want to be minimizing those ones that have to take that longer loop. So we did look at inside into different memory chips at least briefly. And so we have these different address lines that go to a specific memory module. And so that data is then stuff that is reported out or we write. And so all of that is taken care of. And if you look inside a chip, oftentimes they have multiple subchips that are aggregated together. And so like this is a 16-bit DRAM for megabits times 4. And so if I wanted to aggregate that together, I could just have more of these green boxes here and just have a few more address bits, and that's how that would start to grow that way. This is another way of looking at now, instead of just thinking about all different aspects of memory that we saw in this earlier chart, now we're just focusing on RAM. And so here we can have higher performing things, increasing performance and endurance, versus going down lower level, it's slower. And so you can see hard disks faster would be a NAND flash or an SSD. And then you can be going up in this direction, getting closer to what you would be having for registers. This is a layout for a hard drive. So a platter, so an HDD. And so these are the terminology that we looked at for how you can locate it in a certain place. You have heads that are on top and bottom. And so they can be reading that data as this thing is rotating. And so once per revolution, it's going to be seeing different sectors and different tracks. We also mentioned RAID level. So I'm just going to mention the first two. You can either just say you have stripes, and so you have 2 hard drives and you have 1 stripe for the first one, 1 stripe for the second one, then you have the second stripe for the first one, the second stripe for the second one. That would be one way. So there's no redundancy, but the highest level of redundancy is it's literally mirrored. The same information is put on 2 disks, and so it requires twice the number of disks to perform that, but your stability of the information is a lot higher. Last time we talked about I/O devices, and so basically you have this translation element that it hooks into the system bus and it links to the peripheral, and this is where all of the coordination, translation, and what have you takes place. This is a more detailed look, and so you have the side that is facing the computing environment here, and you have the side that is facing the peripheral or the I/O device, and it needs to be doing this translation, buffering, and stuff like that. So that's what we have covered up to this point. For this chapter, I'll just finish with this chart and then get into the details. So we're going to be talking about the operating system, and so it fits into a layer that you have your libraries and utilities, and finally your applications are above that. So this is the software part, and so the computer science, computer information folks would be more familiar with that end, but you also have the hardware where this gets into the specifics of how we're going to be building that. And so your von Neumann architecture, your CPU, your memory, your input and output, and all of that, that's here that we have here underneath that in the hardware portion of our architecture. Any questions on that? It should just be review. So any questions from those online? Yeah, just a second. Why, for those that are online, why don't you just give me a thumbs up if you're tracking? Okay, good. Yes?
So the hardware, just for clarification, the hardware is like just the processing of like memory, and then like software is like what controls like the
Yeah.
hardware what to do
Mm-hmm.
to process this type of memory, or
Yeah, you'll get a chance to see this a little bit more when we start playing with our Arduino units. The Arduino unit itself is a hardware,
Yeah.
but then you can load a program into it, and that's software. And so you can see that the hardware and software start to work together. But hopefully, as a result of going through material in today's lecture, it'll fill in some of those blanks and help you get a chance to see this. So now we're thinking about operating system support, but in the context of what we see here, we can see we've been building on all of these memory things. Now you need someone that needs to be a clearinghouse from the software side of doing the coordination and making sure that things are happening the way you would like. So we'll start with focusing on an overview of what an operating system is. I think some, if not most of you guys will be taking an operating system course, which one of the textbooks that I really like looking at is pretty interesting. Thinking about that, talk about the different types of operating system. We'll talk about scheduling. So this is where you can really improve the utilization of your system just by making sure that your scheduling is as best you can. There's then we have a couple of different memory management approaches. The x86, the Intel x86 approach. We have the ARM memory management approach. And then we just have some other general memory management things of how we can be thinking about different parts of what we're exploring here. This is a chart that I showed in the overview section. You can see how the software sits on top of the hardware, at least in terms of you can be thinking about how it works in this diagram here. We'll be talking about these three different topics here in a couple charts. The instruction set. So this is how you guys are getting a chance to see what assembly language programming is like. And so this will be thinking about the instruction set of how to engage directly with the CPU and the arithmetic logic unit within that. There's the application binary interface. And so this is where you have this connection between the operating system and libraries and stuff like that. And then finally, the way that the different applications connect with the operating system and other things is the API or application programming interface. And so we'll come to this in a minute, but just a little bit of perspective with a nice pictorial there. So the operating system services, it's the most important system program. And so for a personal computer, a tablet, a cell phone, they all have operating systems. And so that's the way that we have our modern devices. They need to have some kind of base operating system. So it masks the details of the hardware from the programmer and provides a programmer with a convenient interface for using the system. So a programmer doesn't need to know all of these details, just as long as they have the right APIs to know how to plug into, that's it. The operating system typically provides services in the following areas: program creation, so software developers, program execution, managing that things are going on okay, access to the input and out devices, controlling access to files. So the operating system is going to have access to more things than other parts of the computing system. The overall system access, error detection and response, and accounting. So there's just all kinds of stuff that are going on. So I mentioned these three things over here on this chart. This just gives a blow up of those. And so you're going to get a chance to work with the instruction set architecture with our MIPS assembly language. And I've showed a couple sample programs during our lab time on Thursdays. And so we'll keep doing that as we go along. And hopefully that will give you some more insight into that. So so that's the ISA, the API. That's how we get the software modules to be communicating with each other. And then we have the application binary interfaces. You have like a library that's already been compiled. And so you need to have the way to know how those things work together. And so those are the three things that we're conveying. So the operating system acts as a resource manager. And so it's a conductor, if you will. So a computer is a set of resources for the movement, storage, and processing of data, and for the control of these functions. The operating system is responsible for managing these resources. The operating system as a control mechanism is unusual in two respects. The operating system functions in the same way as ordinary computer software. It is a program executed by the processor. The operating system frequently relinquishes control and must depend on the processor to allow it to regain control. So this is just an illustration of the operating system acting as a resource manager. And so this suggests the main resources that are managed by the OS. A portion of the OS is in main memory. So this includes the kernel or nucleus, which contains the most frequently used functions of the OS, and at a given time, other portions of the OS currently in use. So you guys have all heard the term kernel. Is that something that you're familiar with? Let me just check for those online. Is that something, a term that you guys are familiar with? Good. So some of you are familiar with that idea. That is the guts, the primary thing that the operating system uses. And if any of you are familiar with Linux, it's kind of interesting to track the kernel that they're leveraging. I have a couple servers and other things that use Linux. And so periodically they come up with a new kernel, and you can get some insight into that. And so that's what's largely is doing the extreme immediate things going on that the operating system does. Well, there's two types of way that you can be interacting. So you can either have a interactive system. So this is a user program to interact directly with the computer. User may, depending on the nature of the application, communicate with the computer during the execution of the job. So that's possible, but a batch system. Anybody ever heard of batch? Do you guys familiar with that? So it's both old and new, to give you an idea. And we'll talk a little bit more about this. So it used to be that you'd have to submit a job, and then the computer would take that information with all the other jobs. It would assign a time for it to execute, how much time it would be allocated to do that, and then report back that information. So nowadays with cloud computing, it's just sort of have some way of a resurgence that you send things to a virtual server, you have it do things, and when it's done, it reports you back the information. So in the very early programming, there wasn't any operating system at all. So it was like you're working directly with aspects of what's going on in the computer environment, and it has one instruction at a time that it tells it what it's supposed to do. So the problems were scheduling. Sign-up sheets were used to reserve processor time. You can see that's probably not going to be very efficient. The setup time, a single program could involve loading the compiler plus other things, saving the compiled program, loading and linking together the object program and common functions. So it would be that you would submit a job, and then you go to the computer room, you'd find your last name, the bucket which have your printout, and you get your printout, and that's where you need to find out if it worked or if you need to fix an error, and then come back and submit it again. So here's a memory layout for a resonant monitor. And so here our early processors were very expensive, and therefore it was important to maximize processor utilization. The wasted time due to scheduling and setup was unacceptable. So to improve utilization, simple batch processing systems were developed. And I got a chance to be mentioning a little bit about that in the previous couple of slides. So the processor executes instructions from the portion of memory containing the monitor, monitoring where it is. The monitor handles setup and scheduling. Then we have this job control language that manages various jobs that can be run. And so here's just an example. So a list of the types of commands that this JCL would have. And so each Fortran instruction and Anybody ever heard of Fortran? Is that probably maybe, or maybe that's something that you guys haven't even heard of. So this was probably a huge workhorse for technical computing for a long time. There actually still are some modules that are written in Fortran. Some of you guys will be taking software engineering in the future, and the idea of refactoring a piece of software that's already been validated is something you tend to avoid. So maybe you might have a virtual machine that would be still running at Fortran and integrate with that. So you have the JCL, and then you with the monitor or with the batch operating system, you're able to go ahead and run these computer programs. Here's are some desirable hardware features. You have memory protection. The user program must not alter the memory area containing the monitor. And so you have your protected status for your operating system, that you are the only person that can, you being the operating system, that can, only one that can deal with that area. You have a timer. It's used to prevent a job from monopolizing the system. And so you have an infinite loop. You want to cut it off, and so you can get back to giving share to everybody. There's privileged instructions only that can only be executed by the monitor, so a overall monitoring of everything. And then you have interrupts. It gives the operating more flexibility to relinquish control and to regaining control from user programs. So this just gives you an idea of a utilization example. You do read one record from a file, execute 100 instructions, write one record to a file. So in 31 microseconds, so the percent of the CPU utilization is only on the order of like 3%. So this is where we got into this kind of a strategy where you do multi-programming. And so all of the clear ones would be A, the lightly shaded would be B, a little darker shaded would be C. And so thus you can see, if you put all these things together, you're going to improve on this percent of the CPU utilization. And so there's been strategies to try and help that out. And so you can have the characteristics of different types of jobs and the things that they need. And so, well, what are we going to do? How are we going to put those things together? So here's just showing a chart. If we were to do this multi-programming, you can see it's like twice as good by various factors. Processor use is twice as much. Memory is used twice as much, so you're not having resources going to waste. And so here is the uni-programming approach. And so according to this, it takes 30 cycles here, but if we do it in this multi-programming approach, we can cut that in half. And so this is just like maybe a little bit easier to see as compared to the information that we have in that table there. So that's a little bit of motivation for now. We have some operating system things that are helping us conduct and utilize our resources better. For time sharing systems, it is used when the user interacts directly with the computer. So this is more what we're used to today, a server and user paradigm. So the processor's time is shared among multiple users. Multiple users simultaneously access the system through terminals. So this would be like you're communicating directly with a mainframe for that, with the operating system interleaving the execution of each user's program in a short burst or quantum of computation. So that just gives you an idea of how that would work. So so what are the principles for batch? Is you're trying to maximize the processor use. The job control language commands provided with the job. And so that's the thing that we have here. And then for time sharing, that you're trying to minimize the response time, and commands are entered at the terminal. So you were seeing a migration of going from one kind of concept to another. And so I have some more detailed charts for each one of these. And so these are talking about the types of scheduling. So you have long-term scheduling, the decision to add to the pool of processors to be executed. So more things are in the queue. Medium-term scheduling, the decision to add to the number of processors that are partially or fully in main memory. And so you have some of them in this cache, if you will. And so which one's going to load first? Maybe you don't have enough room for a big one, but you could stick a medium one. And then finally, short-term scheduling. This is a decision as to which available process will be executed by the processor. And then finally, I/O scheduling, the decision as to which processes pending I/O requests shall be handled by an available I/O device. So since we have a lot of folks online today, let me just do a scan. Are folks tracking with what we have here? Does what I've talked about, what an operating system does, the idea of scheduling, you getting a perspective on that? Okay. Sounds good. So then this is just some more details about these different things. And so the long-term schedule determines which programs are admitted to the system for processing. Thus it controls the degree of multi-programming. Once admitted, a job or user program becomes a process and is added to the queue for the short-term scheduler. Here we have the medium and short term. We just talked about that. The medium term schedule is part of the swapping function. Typically, the swapping indecision is based on the need to manage the degree of multi-programming. The short-term scheduler, also known as the dispatcher, executes frequently and makes the fine-grained decision of which job to execute next. So anybody baseball fans here? Maybe I'll just go in the line. You have one or two. Anybody online? You want to give me a thumbs up if anybody is tracking as we're getting towards the end of the Major League Baseball? Okay, at least maybe not that many, but some people like it. I have a little bit of enjoyment with that. So a short term is more like you can think like a shortstop or first baseman or something like that. Maybe your longer term would be more like an outfielder. And so the folks in the infield, they're having to service things a lot, but you need them to all work together to make things happen. And so thus having each one of these schedulers all has their piece for making things work well. So this just gives you a pictorial of a scheduling 5-state process model. And so you have something that's admitted, and then you have to figure out, well, what are we going to do? Can we get it running? Do we have to wait? And so this is a block trying to help us understand what the short-term scheduler is actually doing. To understand the operation of the short-term scheduler, we need to consider the concept of process state. During the lifetime of a process, its status will change a number of times. Its status at any point in time is referred to as a state. So is it blocked, running, ready, just admitted, or completed? You can see things like that. This is the processor control block. For each process in the system, the OS must maintain information indicating the state of the process and other information necessary for process execution. For this purpose, each process is represented in the OS as a process control block. We're showing that here. So we have the identifier, the state, the priority, the program counter, memory pointers, content, data, I/O status information, counting information, and stuff that could go beyond these basic things that are all wrapped together into this data structure of information that's trying to capture what's going on for a process. We can have, now we can, then get into the scheduling. For an example, to understand how the OS manages the scheduling of the various jobs in memory, we can begin by considering this simple figure. And it shows how main memory is partitioned at a given point in time. The kernel of the OS is, of course, always resident. In addition, there are a number of active processes. So you can do it on both of, well, you can do it on a Mac, you can do it on a PC, you can do it in Linux, and you can actually check the processes on you running in your computer. And so this is maybe gives you a perspective of like what's going on here. You can see sometimes you may have a stale process. Maybe you'll try and stop a process. Those are things that you could be doing. So here are some key elements of an operating system for multi-programming. This simple example highlights the basic functioning of the short-term scheduler. The figure shows the major elements of the OS involved in multi-programming and scheduling of the process. So the OS receives control of the process at the interrupt handler if an interrupt occurs, and the service call handler if a service call occurs. Once the interrupt or service call is handled, the short-term scheduler is invoked to select a process for execution. You can read more about this in the textbook, but I just wanted to give you a little bit of an overview about that. So this figure suggests how processes progress through the computer using the control of the OS. Each process request, then a batch job, user-defined interactive job is placed in the long-term queue. And so you might remember we had a couple of figures and diagrams showing that earlier, the different types of the schedulers. So this is it getting loaded specifically into our resources. Here we have the use of swapping. So you can look over that a little bit more, but I won't dwell on this too much here. So here is an example of a fixed partitioning of a 64 megabyte memory. So is this the best way of utilizing your memory? So we have equal size partitions. Here you have unequal size partitions. So you can allocate some memory. Do you want to allocate this level? What if you need more, then do you allocate two of them? Or do you just want to allocate exactly what you need? Those are some examples of choices that you could be having. Then we have dynamic partitioning. So we can get into this where you, instead of having a fixed amount, you the process tells you how much it needs, and then you find a good place to put it. And so this is reflecting on this type of information that it's then going to allocate the resources that you need. So the operating system is a conductor, and it's basically going to walk you through. It's going to be active until it completes. Then it releases that memory and it can be used for something else. This is just as another thing that you can have. And so you have both unequal sized and variable size partitions are inefficient in the use of memory. Suppose, however, that the memory is partitioned into equal fixed size chunks. And so you have something that's in the middle. It's not quite going that you have fixed, or it's not quite that you just allocate exactly what you need, but instead we want to be allocating chunks is another alternative. And so you basically have it that way. So it's kind of a middle of the road way of trying to optimize resources. Then we can have logical and physical addressing. And so suppose as what we're trying to describe here, that there are not sufficient unused contiguous frames to hold the process. Does this prevent the OS from loading the whatever we're trying to execute? The answer is no, because we can once again use a concept of logical addressing. So we find a little piece here, we find a little piece there, and we could stitch together and as a result, voila, find enough room to run this process, even though it may not be the cleanest, it's just a one contiguous area of memory for us to utilize. So I've used this term periodically. Anybody familiar with the term virtual memory? Does that make sense to you all? There's a variety of ways that we can be thinking about that, but is that a term that you guys are familiar with? Just give me a thumbs up if you have heard of it. Okay, at least a few of you have heard of that as an idea. And so it's not the real address. It's like instead of giving the street address for this building, say I'm in building 1. And so folks at APU are familiar with that. And so that could be an example of a virtual way of providing an understanding of where we're going. And so here now we're not actually giving the real address or something like that, but we're trying to think about it from a different point of view. And so paging would be part of that. So with the use of paging, truly effective multiprocessing systems came into being. Furthermore, the simple tactic of breaking up a process into pages left the development of another important concept, virtual memory. So to understand virtual memory, we must add a refinement to the paging scheme just discussed. That the refinement is demand paging, which simply means that each page of a process is brought in only when it is needed, that is on demand. So maybe you can think of like a page in a book. The information you have is on that page. It may not be the whole page, but it's part of that page. And so that is something that we get a chance to start to see how that might work. And so say if you're on a street, and so maybe there's 10 people on your side of the street, and so at least you're getting the one that you want, but you're getting some other ones as well. So an alternative approach to the use of 1 or 2 level page tables is the use of an inverted page table structure, which we're showing in this figure. Variations on this approach are used on the PowerPC, UltraSPARC, and the IA64 architectures. And so those are some things. PowerPC used to be the processor that Apple had. UltraSPARC was something that Sun Microsystem that got bought by Oracle used. IA64 architecture is one of the architectures that Intel has developed. But there's other things like that. In this approach, the page number portion of a virtual address is mapped into a hash value using a simple hashing function. The hash value is a pointer to the inverted page table, which contains the page table entries. And so thus we can see that we have this memory available to us, and we create a hash, and this is going to direct us to a certain piece or multiple pieces of memory for our use. And so that gets a little bit more complicated, but just gives you an idea as we're going a little bit deeper into some of these things. We have the operation of paging and the translation lookup buffer, the TLB. So in principle, then every virtual memory reference can cause 2 physical memory addresses, one to fetch the appropriate page table and one to fetch the desired data. So you get the page and then you get the line number if you want to use that analogy of something in a page in a book. We can also have the translation lookup table and cache operations. So we've talked about cache operations before. Now we can be seeing how this could be something that may help us to make this performance a little bit quicker. We may not have to go all the way to the main memory. We get this, we want to get this page out of the book. Is that something that's already loaded into the cache? If so, we can go ahead and send that. Otherwise, we have to go out to the main memory. So there's another way to which addressable memory can be subdivided, known as segmentation, where paging is invisible to the programmer and serves the purpose of providing the programmer with a larger address space. Segmentation is usually visible to the programmer and is provided as a convenience for organizing programs and data, and as a means for associating privilege and protection attributes with instructions and data. So this is another thing that's laid out here in the textbook. I'm just going to scan forward for a second. So the advantages, it simplifies the handling of growing data structures. It allows programs to be altered and recompiled independently without requiring an entire set of programs to be relinked and reloaded. It lends itself to share among processes, and it lends itself to protection. We have how this is done in the Intel x86 approach. It uses both hardware, it includes hardware for both segmentation and paging. It has unsegmented, unpaged memory. It has unsegmented page memory. It has segmented unpaged memory, and it has segmented paged memory. So basically, you have a lot of different things that are used as part of this x86 architecture for Intel. This just gets into a little bit more detail in terms of segmentation. Each virtual address consists of a 16-bit segment reference and a 32-bit offset. Unsegmented virtual memory is 2 to the 32, which is 4 gigabytes. Segmented virtual memory is 2 to the 46, 64 terabytes, and so that's a lot of memory that's available. So the physical address space employs a 32-bit address for a maximum of 8 gigabytes. The virtual address space is divided into two parts. One half is global, and is shared by all processors, and the remainder is local and is distinct for each process. So this gets a little bit complicated here. And maybe let me pause for a minute, and I'll go back to the contents for this chapter and see if anybody has any comments or questions on what we have addressed so far. We talked about operating system overview. We talked about scheduling. We talked about those 3 different schedulers. We then walked into Intel's x86 memory management. And so this is one example of an implementation. You guys tracking on that? You can either tell me here, or for folks online, just do a heads up if that makes, yeah. Are you understanding the concept of why this would be helpful? Does that make sense? Yeah? Okay. Get my place again here. So the address translation mechanism for segmentation involves mapping a virtual address into what is referred to as a linear address. A virtual address consists of a 32-bit offset and a 16-bit segmented sector. And so this is trying to give us a little bit of a sense of what that would look like. So that's this top part of this figure. An instruction fetching or storing an operand specifies the offset, and a register containing the segmented selector The segment selector consists of the following fields: table indicator, segment number, press privilege level. So those are all things that are there. Well, this gets a little bit more complicated, so I'm just going to keep it at a high level. This is something that you can read installing to get more details about this. So these are the x86 memory management parameters. You can see that this is now another area of complexity. We talked about cache, we talked about buffers, we talked about virtual memory, and now we talk about memory management and possible ways of doing that. And so that's the Intel approach of what they're looking at. So segmentation is an optional feature that can be disabled when a segmentation is in use. Addressing used in programs are virtual addresses and are converted into linear addresses. When segmentation is not used, linear addresses are used in programs. In either case, the following steps is to convert that linear address into a real 32-bit address. So eventually you have to get into a real address to locate it. So then we get into the two-level page table lookup. And so this just gives a strategy for how we're going to accomplish that. This is an illustration of the Intel x86 memory address translation mechanism. So it illustrates the combination of segmentation and paging mechanisms. So we can be doing a lot of things that can be helping us without manage our memory. Okay, the last thing that we get a chance to be thinking about is the ARM memory system overview. And so this is another manufacturer that created this general way, just like AMD also does things like Intel. ARM has multiple places, multiple manufacturers that implement this general high-level category of architecture. So ARM provides a versatility virtual memory management system architecture that can be tailored to the needs of the embedded system designer. So ARM is typically more focused towards embedded processing. x86 is more for desktop applications, although it's kind of blurred over time. And so this just gives us you an idea of what would be done. You have the memory management unit here, dealing with a ARM core part of the processor, and you have caching that's laid out here, the TLB that we mentioned earlier, and ultimately it has to be converted into a physical address where it's loaded in main memory. And so thus we can see there's multiple layers of what this memory management unit is doing before it gets to that actual physical address, and then relaying that information to the processor core over there. That figure is probably the best thing to focus some time on versus maybe some of the other things that we're doing. So the ARM supports memory access based on either sections or pages. So you can either have super sections consisting of 6 megabit blocks, sections consisting of 1 megabit blocks, large pages, 64-bit kilobyte blocks, or small pages that are 4 kilobyte blocks. Sections and super sections are supported to allow mapping of a large region of memory while using only a single entry in the TLB. So I think we've gotten enough insight to be thinking about this and how it is done a little bit differently than the x86 approach. This shows the ARM virtual memory address translation for small pages. This is the ARM memory management formats. And so if I was just to cycle back between the formats that are used there, I think I got the right. Here's the one for the x86. So maybe in principle, they have some similarities, but there's a lot of details that go into each one of these. So to get a better understanding of the ARM memory management scheme, we can see that the key formats that are shown in this figure, the control bits shown in this figure are defined in table 9.6. And this we have here. So just like you have those two charts together. Then we have the x86, but there's enough things in the x86 architecture. It takes two tables to cover all of the things that are done with its memory management. So then we also have access control. The access permission AP access control bits in each table entry controls access to a region of memory to give a process. A region of memory can be designed as no access, read only, or read and write only. So guess what? If you have your program loaded in your computer, you want to only provide read only to the user. Protected memory would be the things that the operating system is going to use. The region can be privileged access only, reserved for the use of the OS and not by applications. The ARM employs the concept of a domain, collection of sections and or pages that have particular access permissions. The ARM architecture supports 16 domains and allows multiple processes to use the same translation table while maintaining some protections for each other. Two kinds of domains access are supported. You can either have clients or managers. The clients, the users of domains that must observe the access permissions of the individual sections and or pages that make up the domain, and managers control the behavior of the domain and bypass the access permission for table entries in that domain. Okay, so we got a little bit technical there, but let's just kind of come back and be thinking about this, and then we'll go one layer up to the table of contents for our textbook here. So we're thinking about operating system support. And so we talked about the different types of operating systems. A batch or an interactive would be the two. We talked about scheduling. And so there's three levels of scheduling, how you're trying to take processes. And so the CPU is the hardware companion to the operating system that then determines what's going to go where and allocate those resources to specific processes. Then we had a lot of different things that we talked about in terms of memory management, the address space. We talked about segmentation and paging. And so this is for the Intel x86 memory management approach. We then got a chance to talk a little bit more about concept and management, memory management. So there's the swapping in addition to the paging and segmentation we talked about here. So swapping, partitioning, paging, virtual memory, the TLB, the translation look-aside buffer, and segmentation. And then we can see the memory management for ARM. And so we got a chance to be thinking about the memory system organization, the virtual memory address translation, the memory management formats, and the access control. So let me just do a roll call. Any comments or questions on that? Does that, you guys following with what we've got there? Nathan?
Say clarification on this, like, of the operating systems work? Like batch, and there was another one.
Interactive.
Yeah,
So what's the difference between the two?
or like just like Yeah, like kind of like how do they function? Too.
Let me go back. So here are the two types, and first is the interactive system. This is the one that we're used to. And so the user is interacting directly with the operating system. A batch is you submit a job, and then it's put into the scheduler that the operating system uses and makes it happen. And when it's done, it goes back and says, I'm ready to take another job.
So it's like, is this one? So it's saying like the user's program is batch together. So that's when like after we create this program, that it will then like we can let it do the work
Execute
itself.
it, then you want to have it executed. So it's one thing to write a program, but then the next thing you want to do is to run that program, execute that program. So there's two different ways. And so here you just push the button and it does it. Or here you send it to the server and you have to wait for the server to schedule it time for it to execute it and then complete. Does that make sense?
A little bit. I mean, I get the interactive one, just the batch one, just a little bit. I mean, I can see that like, um,
Well, just think of it maybe I'm sure you all like to go out to eat restaurants. And so
Yeah.
what do? You tell your server what you want to eat.
yeah,
Well, they have to go back and make it. And so back in the kitchen, they have a line. Who was the first person that came in? Okay, I make this guy's pizza, then I'm gonna make this guy's steak, this guy's hamburger. And so there's a queuing system that's put in there. So that's kind of like what we're seeing that's going on here. That's more of a batch interactive type of mode. You could be thinking of that. And so, um,
Oh.
okay, does that make sense?
Oh, so it's like, so it's a program that we send out to the computer that is then taken to a list with other programs
Right.
that are to
Yeah.
be executed.
All kinds of users are engaging with that server. And that server is scheduling all those programs in some type of order scheme, priority scheme, or it's a combination of when you submit it and the priority that you have to figure out when you're going to be executed, how long it's going to take, what kind of resources it needs, stuff like that.
And the interactive is like, oh, we just do the program. And
Yeah.
just
Right.
submit the
More
program.
like your personal computer kind of environment.
Yeah. Okay.
It kind of
Alright,
gives you
yeah.
a comparison. So that's the operating system. Then we can see that there's, just like caching, it turns out that having multi-layers of scheduling actually help to make it perform better. Okay, so there's a long-term, medium-term, and short-term to to break that down and to make that work. Okay, then we have the memory management. And so the way that a CPU sees memory is different than the way that an input and output device sees memory. And so how do you allocate memory from one device to another? All of that is something that something that you can vary as well. So we saw that the general nature of how you go from say between a program or data is different. So we can see that that's something that is different. We get a chance to see a little bit of that when we start to think of the memory management. And so we talked about two manufacturers' approaches for memory management, the x86 and the ARM memory management. You could spend a little bit more time with a textbook to be thinking about those, but we're trying to both give some general concepts as well as talk about some specific implementations. And so all of these things are possible. How much you can allocate, how long are you going to allocate it? Are you going to break it up into pages, like a pages in a book, so you don't get the individual line, you get the page that it's on in the book? the way that a CPU sees the memory is more of a virtual way, and you can be having some flexibility of how you're going to make it the most efficient. So we're trying to have efficient use of the CPU. We're trying to have efficient use of the memory as well. And you can see just by this chapter that there's a lot of complexity that can start to be rolled into to make that happen. Any other comments or questions? For those that are online, is that helping, just making have a little bit more clarification, giving a larger perspective on memory management? Okay. And so this is going to be finishing up that next major section, the computer system. And so the next thing we're going to be talking about is going to be closely related, but in more depth, what we do with our digital logic designs. And so now we're going to get a chance to be thinking about how we can be programming in hardware. And we'll get more information, more insight into the arithmetic logic unit. Anybody remember me mentioning the ALU, arithmetic logic unit? Is that something that you guys remember? At least the term. We haven't got into the guts of that, but that's in some of these diagrams that I've shown you. It's kind of starting to come out of the woods a little bit here. Go back to the well, we're going to get into it in detail in chapter 11, but there was a earlier chart where we were starting to look at it a little bit here. And this little thing here, this execution unit, without calling an arithmetic logic unit, that's literally what we're referring to there. So it's amazing to think, how did we ever come up with computers in general? And to make it a reprogrammable rather than you only can do one thing. So you have this creation of software and the engagement with the user to have it do a lot of different things. We're so used to having that in our day-to-day life that it's hard for us to be thinking about. There was a time when that wasn't available to us. Okay, well, on Thursday, we'll be getting into arithmetic and logic. And so we'll, about that point where people can start sharing their digital logic designs. And I'll also continue to be giving some more examples of assembly language programs so we can get familiar with that. Once we get through the arithmetic and logic section, this is where we'll get into the stuff for the assembly language, the instruction set characteristics and functions. And so we'll get a little precursor of that with what we're trying to do with some of our lab time. Okay. I think that's probably a good breaking point. Anything online? You guys tracking? Okay, good. All right, have a good rest of your day. We'll talk to you soon. Take care.